Okay, now we get to the fun part where we actually get to analyze some systems with levers using math and equations and physics. Um, this is the good part of engineering. There's one thing that we need to talk about before we can get into analyzing the systems, and that is the difference between torques and moments. And in reality, there's not a lot that's different. So the definitions that we have, a torque is a force that produces or tends to produce rotation or torsion. Torsion is a fancy word for twisting. Engineers like to have fancy words. And one of those fancy words is moment. So a moment is the rotational effect or the rotating effect caused by a force about a point. Now, in reality, torques and moments are kind of used interchangeably. But more commonly, what you'll see in engineering is moment. So we want to just get familiar with that word so we know it's very similar to torque. It's what causes the system to rotate. Okay. Um, Now, how do we actually calculate the moment that's produced by a force? Because we'll see systems where we have forces acting and nothing's moving, um, and that's because the moments are balanced. And we have to figure out what are the moments equal to. So the moment is equal to the magnitude of the force times the, let's see, that's it, perpendicular distance from the point to the line of action of the force. So the moment is just the force times the distance. Now, one thing to note is that moments have the same units as work, same base units as work, but they are not interchangeable. Moment is not a measure of energy. Interchangeable. And this is the perpendicular distance. So what does that mean? Perpendicular distance from the point to the line of action of the force. So let's look at just a simple lever. We've got our fulcrum in the middle. And now anytime we do a moment calculation in this class, we're going to use the fulcrum as our point of interest. That's where we're going to be taking the moment from. So we want to see how far away are our forces from the fulcrum. Let's say that this is our load and this is our effort. Now, the line of action of the force, that's just if this force were to continue in a straight line, right? It would just keep going down like that. So we want to find what's the perpendicular distance from this point to that line. And so, you know, we did that in geometry as well, where we found the distance between a point and a line. It's going to be a lot simpler here because most of the time we're just going to see a force acting vertically, um, kind of tangent to the point of rotation. So this right here would be the perpendicular distance, right? Because if you go out from the center to the force forms a perpendicular or a right angle with that line coming from the fulcrum. That's all it is. So let's do an example. Let's actually calculate the effort moment acting on the following lever. So we've got on the left side, we've got a 15 Newton force that is 6 meters away from the fulcrum. So if I want to find the moment caused by the effort, we'll call it ME. That is just the force, 15 newtons, times the distance, the perpendicular distance. And again, since the force is acting vertically, we can just use the 6 meters. And so that's just going to be 90 Newton meters. There's your unit for moments in SI. Now, what that actually means is that you have a 90 Newton meter moment that wants the bar to rotate counterclockwise, right? If I were to keep pushing this down, it would spin about the fulcrum going in that direction. Okay, and so we call this a counterclockwise moment, and we'll just abbreviate that as CCW. Now, the resistance or the load, if we were interested in that, would cause the lever to spin clockwise about the fulcrum. So that's a clockwise moment. Okay. Why is that important? Because when the counterclockwise moments and the clockwise moments are equal, then we say that the lever is in static equilibrium or rotational equilibrium. So when the sum of all the moments on a lever equals 0, the lever is in rotational equilibrium. And again, rotational equilibrium is the state in which the sum of all the counterclockwise moments equals the sum of all of the clockwise moments about a pivot point. In this case, the fulcrum. We're always going to use the fulcrum in this class because by doing that about the fulcrum, we can ignore any reaction forces caused by the fulcrum itself. Okay, so let's look at an example, or let's build off that example we were going with. So let's assume that the lever is in rotational equilibrium. So the counterclockwise moment created by the effort is equal to the counterclockwise moment created by the load. So the moment created by the effort is equal to the moment created by the load force. How far from the fulcrum would a 30 Newton load be placed if we're in rotational equilibrium? Okay, so let's see, how do we calculate the moment caused by the effort force? Well, we already did that. We know that that was 15 newtons at a distance of 6 meters from the fulcrum. And that's 90 Newton meters. Now, the moment caused by the load force, we know it's 30 newtons at some distance away from the fulcrum. We don't know what that distance is. So for right now, we can just call that x. X is the distance from the fulcrum of the load force. Now this is going to work out pretty simply. 90 is equal to 30x, and so we divide both sides by 30. Sorry, let's keep our units in here. times x. We'll divide both sides by 30 newtons. The newtons will cancel. The 30s will cancel on the right side. And then on the left, we'll get 90 divided by 30, which is just 3. And we'll have meters left. So x is equal to 3 meters. That's how far away you should place the load in order for the system to stay in static or rotational equilibrium. Okay. So we'll do more practice problems with that. You're going to have a worksheet that has 3 different examples and 3 questions for each one. And they'll look a lot like this. So this is not on the worksheet. This is one that I pulled from a textbook, just to show you an example of how to go about doing the problems on the worksheet for today. So we have our example. An 8-foot long second-class lever has a 150-pound resistance force located 4 feet from the fulcrum. An effort force is applied to the end of the lever to maintain static equilibrium or rotational equilibrium. Same thing. It means it's not moving. Not moving. Okay. And one thing to note is that on all of these problems that you'll see on the worksheet, there's going to be an absence of friction. Okay. So we don't need to take into account any losses of energy. And what that implies is that anywhere you see mechanical advantage, it's the ideal mechanical advantage. And if there's no friction, then the actual mechanical advantage is equal to the ideal mechanical advantage. So on these problems on the worksheet, the efficiency is always going to be 100%. So let's sketch and annotate the lever system described above. So we've got a second-class lever. Now, a second-class lever, remember, that has the fulcrum at one end. And then we've got the load in the middle. Think about like a wheelbarrow. Wheelbarrow is a second-class lever. We've got a load in the middle. We'll have that pushing down. And we know that that's 150 pounds. And then we've got an effort force at the other end. We'll call that FE. And let's go ahead and add our distances as well. So we know that from the fulcrum to the resistance force is 4 feet. And the entire length of the lever is 8 feet. Okay, so that's the distance of the effort force to the fulcrum. And that's about all we want to do, right? You want to indicate your fulcrum, your load, the distance, and your effort force. Just pretty much include everything that you have there. Then we want to do some calculations. So the first thing it asks is, what's the mechanical advantage, the ideal mechanical advantage of the system? Now, if you remember back from last time, the ideal mechanical advantage, we have the expression, I'm a deer. So the ideal mechanical advantage is the distance covered by the effort force to the distance covered by the resistance force or the load. And we talked about how we can use the circumference to figure out a ratio of how far these forces travel. But what it simplified down to was it's really just equal to the radius of the effort force from the fulcrum to the radius of the resistance force or the load to the fulcrum. I always do lower e's for some reason there. So all we need to do to calculate the ideal mechanical advantage of this system is plug in what we know. We know that the radius of the effort force from the fulcrum is 8 feet. And we know that the radius of the resistance force or the load from the fulcrum is 4 feet. And so that gives us an ideal mechanical advantage of 2. So any force we put in is going to be doubled, right? It's going to increase the magnitude of the effort force when we're looking at the system. Okay, and now using static equilibrium calculations, calculate the effort force required to keep the load from dropping. So in order to maintain equilibrium. So remember, we want our moment created by the effort force to equal the moment created by the reaction force or the resistance force. Because if we look at what those are doing in our graph, the effort force is going to cause the system to rotate counterclockwise, right? And the load would cause the system to rotate clockwise. Okay, and we want those to be equal to each other in order for the system to stay balanced, stay in equilibrium. So the moment caused by the effort force is going to be the effort force times the distance from the fulcrum, which we know is 8 feet, and the moment created by the reaction force is equal to the load or the resistance force. Sorry, I keep saying reaction. I mean resistance. The resistance force, which is 150 pounds, times its distance from the fulcrum, which is 4 feet. Okay. Now we can work this out. So we've got FE times 8 feet is equal to 150 times 4, that's 600 foot-pounds. And then we would divide both sides by 8 feet. So FE is equal to 600 feet pounds divided by 8 feet. The feet are going to cancel out. We can do 600 divided by 8, which 75? Don't quote me on that. Let's see. Let's just do it real quick. 8, this goes in not 8 times, it goes in 7 times. 56, 40, 0, 75. Yeah, okay. So the effort force would be 75 pounds. Right? So we only have to put in half as much force as we would have if we were just trying to lift up the load, right? Because the load was 150 pounds, but instead we only have to put in 75 pounds for the effort force. Now, another easier way that we could have done this, they asked us to use the static equilibrium, so that's what we did. But because the ideal mechanical advantage is equal to the actual mechanical advantage, and we know that the ideal mechanical advantage was just 2, the actual mechanical advantage we calculate, you can use the acronym AMI free. And so that is the resistance force over the effort force. And so We multiply both sides by the effort force, so 2 times the effort force is equal to the resistance force. Divide both sides by 2. Effort force is equal to the resistance force divided by 2, which is 150 divided by 2, which is 75. So that's another way that we could have done it. This is only true because no friction. So that's basically what you'll see on the worksheet. Problems that look like this, 3 steps. You'll sketch and annotate the system. You'll find either the ideal mechanical advantage or the actual mechanical advantage, and then you'll do some sort of static equilibrium calculation to figure out the missing value. So all the problems will follow this basic formula for the levers. That's about it. If you have any questions, let me know. You can go ahead and start working on that worksheet. We will only do the first 9 problems that are concerning levers. Go ahead, write them in your engineering notebook, and once we complete that worksheet, once we get through the other 2 simple machines on that worksheet, then we'll turn everything in.